Okay, here's the quick review video that I promised y'all. I'm sorry it's taken so long to get it up, but hopefully this will run you through it. Third period, you'll have to watch it at home. I apologize again. All right. So some of the math stuff that you do need to keep in mind and remember. Accuracy versus precision. Please remember that accuracy happens to be your rightness or how correct you are to what is accepted. And precision is consistency. So when you look at data, you're looking at, does the average come out to where it's supposed to be? And for precision, you're looking for, is the data staying around the same point, measuring the same item? All right, exact versus inexact. So an exact number is a counting number, and it is a conversion in the same system, so metric system to metric or American to American. Inexact is going to be conversions among other systems, and these are going to be measuring kind of numbers. So they're going to have decimals in them, okay? And so the thing to remember with that, the whole point of this is that it affects your sig figs. Inexact affects your sig figs. Exact numbers do not. So do not use your exacts to determine your number of sig figs. All right, a quick rundown of your sig fig rules are as follows. So first things first is you got to know how to know which ones are significant. So remember all non-zero, 0, sandwiched or captive 0. Okay, so anything that's between two non-zeros. Leading zeros don't. And trailing zeros count with a decimal only. Once you've figured out what your sig figs are, you do have two separate rules for when you're doing the math, and you will be asked a question where you're going to have to do multiple steps. So make sure you're following your order of operations, PEMDAS, where you are starting with your parentheses, then exponents, then multiplication, division, addition, subtraction, okay? And from there, if you are adding or subtracting, you're going to count up decimal places. And your answer should have least number of decimal places. If you are doing multiplication and division, you're going to count up sig figs, and your answer will need to have least number of sig figs. Okay, so this one's for sure on your test. All right, now for dimensional analysis, please remember that it's all about having your unit will always come down to the right, okay? And then you'll have a conversion to go up to. This is always a conversion. So, for example, if we are going from seconds to days or something like that, you would start with, let me make another one, seconds, then you would have seconds to maybe hours, so you know that there's 3,600 in 1 hour, and then you would have hour come down to the right, and you would say there's 24 hours in 1 day, and so on and so forth, okay? So the big idea here is you want to make sure your units are being able to cancel out with each other, and they're diagonal from each other. The next thing is density with water displacement. So please remember, this is actually straight from your lab. So remember in your lab, you had your graduated cylinder. You filled it up with some water, right? Filled it up with some water. And then you got one of your objects and you put it in there, okay? You had to measure where that water was to begin with, where it went to finish, and you had to take your final minus initial, right? So final volume minus initial volume, okay? And that gave you your volume of your object, okay? Density formula is density is mass over volume, just like that. So if I am solving for mystery mass and I'm giving you a density and you found the volume, remember that these guys just get multiplied together to find your mass. Okay, the density is mass over volume. Don't forget that water displacement means you have to do your final minus initial to figure out what that density was, just like your lab. All right, average atomic mass. So usually what we'll give you here is we'll have a list of isotopes. You might have like hydrogen 1, hydrogen 2, hydrogen 3, for example, okay? And each one has their own little mass. So 1.03, this one will be like 1.998, and this one will be 2.5. Okay, let's just pretend. I don't really know what they would be. But you would have your mass, and then you would have your relative abundances. So we would tell you something like 14% is this one, and 80% is this one. Okay, and then 6% is your last one. When you go to do these steps, please remember, okay, the steps are: first, you bump the decimal over to the left on your percent. Okay, what you're doing is you're dividing it by 100 to figure out what that percent is in decimal form. Next step, you multiply it by the mass. And third step, you add up values. So that would look like this. We would have this decimal, bump it to the left, multiply these two numbers, so you would now have 1.03 times 0.14. You would get a number. You would do that for each line here, okay? And all of those numbers are what you're going to add up to get your answer, okay? Put that off to the side. Looking at this is the other type of problem that I'll give you, where I will give you the average atomic mass already, okay? I'll give you the average atomic mass. I'll give you a percent in one of the masses. What you have to do is then figure out, okay, if this is a certain percentage, obviously 100 minus that percent is the other one, so you can figure that part out, and then you'll solve for the extra mass of the isotope. So you might write down that equation and just look it over. I know you have an example in your packet, so make sure you look at that. It's around the isotope section. Okay, percent composition. So percent composition is pretty easy. Part over whole times 100. And the only thing that makes this difficult is making sure you take care of subscripts. So look at your subscripts for sure. And look at the molar masses, okay? You need a total for this whole. So this is total molar mass. You add them all up. And part is subscript times their individual molar mass, okay? All right, percent yield. We did this one a little yesterday, so remember that this is actual divided by theoretical. Third period. We know that theoretical is what we're going to calculate. It's going to be bigger. So a big indication that you might be doing it wrong is if you have the smaller number on the bottom, okay? All right. And so actual over theoretical, and then you're going to multiply that by 100. So the couple little points about this one was actual is always going to be what you get in the experiment. So typically the way these questions are worded is we give you that piece of information. We say you actually obtained this much. And then we give you information so that you can calculate the theoretical value. Okay? And then you use what you calculated underneath what they gave you in the problem. Okay? And then you multiply by 100. These are sometimes hidden, so make sure you look at the steps prior to that as well. All right, next thing, nuclear notation. All right, so this number right here, this is your mass number. This is not your average atomic mass. Your mass number is made up of protons plus neutrons. This right here is your atomic number. This is equal to your number of protons. If it's electrically neutral, then it'll also be equal to your electrons. This right here will indicate an ion. So this changes your number of electrons. So this one, for example, is a positive. So that means that we are going to lose 1 electron, okay? So knowing all this, if I were to ask you information about its protons, neutrons, and electrons, you would tell me, first of all, you would say this is silver, okay? And its isotope name would be silver 107, okay? It has 47 protons. It has 107 minus 47 neutrons, so we would do that, and you would get 60 neutrons. And then looking here, we would take our proton number, but we're going to lose 1 in order to make it a positive charge, so we're going to have 46 electrons. You do need to be ready to do this, okay? So pay attention to your charges. All right, when you're doing stoichiometry, you will have one that looks like this. Okay, so I'll try and do a quick review over what you want to do. Please remember, you can always fall back on railroad tracks, word down to the right. Make sure you bring that label and unit down, and then you convert going up, and then that'll come down to the right, and you convert going up, okay? So you can use that if you've been trained that way. Otherwise, the shortcut ways are also, if you're going from a mole to a gram, you're going to multiply by its molar mass, okay? If you are going from gram to a mole, you're going to divide by its molar mass. If you're going from a mole over to a chem word, you're going to multiply by Avogadro's number, 6.02 times 10 to the 23rd. If you're going from a chemistry word down to a mole, you're going to divide by Avogadro's number, okay? I should put a little v so you don't think it's atomic number. And by the way, real quick, what I mean by chemistry word would be atoms, molecules, formula units, anything that is not mass or moles, okay? The only thing to be careful on here is if you have a diatomic, such as H2, and they're wanting to know atoms, you have to pay attention to that, okay? Or for mass, you need to pay attention to that subscript as well, okay? So just be careful with your little diatomics. All right, from grams over to chem word, you have to travel through the mole. So you'd have to go from a gram to a mole, just like in this step, and then you'd have to go from a mole to a chem word. If you were doing chem word to grams, I'll mark them with the pink, you would go from chem word to mole, and then a mole to a gram. So those are your steps that you could take, okay? And it's up to you. So when you have your table tomorrow, or not tomorrow, sorry, Thursday on your test, you might be going from molar mass to mass of sample, mass of sample over to moles of sample, okay? So when you do this, this is a mass to mole, so this is divide by your molar mass. You might have to get your molar mass from just looking at your formula. Mass to number of atoms, remember you're going to have to go through it. And then if you need to go backwards, just take a look at, like I said, this little list that I made for you right here. And be ready to do that little chart. That's going to be one that I would recommend practicing at home. All right, empirical and molecular formula. So empirical formula, really easy. So this is the simple one. So simplified. And these are both talking about molecular things, so nothing that's ionic, okay? And this is the true formula, okay? So empirical formula, I usually give you a percentage of things. You're going to change that into a grams. So you're literally going to take your little percent sign, you're going to cross it out, and you're going to change it to be a grams, because you are assuming 100 grams. Your next step is you need to convert grams to moles. And remember, you do that by dividing by its molar mass. That's the quick way. Your next step will be divide by the smallest mole value, okay? And the numbers that you get are your subscripts. Just be careful if you get a 0.5, make sure you multiply everybody by 2, okay? And that's it. So that's how you get your empirical formula. Usually what we would do is we would ask you for an empirical formula and then ask you to then tell us what the molecular formula is. We would have to give you some piece of information. We usually give you the formula weight is, okay? And if we tell you that, okay, that's your molecular formula mass, okay? You have to take you have to find your empirical formula mass. So you're going to add up and you find this. Okay, once you have that, you're going to divide that and you're going to get a ratio. This ratio, you then, so I'll just put CXHY, right? You're now going to take that ratio and multiply it by this entire thing. So let's just say the ratio was 2. You would now have C2X, H2Y. So you're just going to multiply the subscripts by that, okay? All right, limiting reactant. So remember, the whole idea of a limiting reactant is that it's going to run out first. The way to recognize this is if we give you 2 or more amounts of reactants, okay? So if I say you have 50 grams of this and 25 grams of something else, that's your good indication that you're going to have to figure it out. If we use the word excess, then you cross that guy out and don't even worry about it, okay? Excess is like your best friend. But when you are stuck with having to find your limiting reactant, I'm going to go over the shortcut method. What you're going to do is you want to make sure all grams are converted to moles. Sometimes we will give it to you in moles. That's when you just leave it alone. But you need it to be in chemistry language, which is moles. So grams to moles, if you remember, is dividing by your molar mass. Okay. Once it's in moles, you take the mole. You take the mole and you divide it by its coefficient from balanced equation. Okay, well, you do that, and you'll get a value for this one, and you'll do the same thing with your other guy, and you want to figure out who is smaller. Whoever is smallest, that is your limiting reactant, and the other guy will not be. Once you have that, you now proceed on using stoichiometry. Okay? And you proceed with the problem. The long way to do this would have been for me to basically you pick a product and you're going to try each one to see how much product is made, and you want to so if we had A plus B yields C plus D, right? Let's just say we have that, and these two we have values for them. We would pick one of our products, so I'll pick C, and I'll say, okay, if I start with this, how much am I making? If I start with this, how much am I making? And the smaller one is the one to use. Okay? Okay. Balancing, please make sure you practice this. Message me if you need some help. I'll try and put up a resource of some other people, the way they balance things, because I showed you in class how I do it, but this might help if you see another way. Stoichiometry. So this is your big outline. This is the longest one that you would have. This is a gram to gram conversion here. You can also start here, and you can have a mole to gram conversion. You could start here and have a mole to mole conversion. Okay. You can start here. Let's see, where else could we start? Nope, that'll be it. That'll be it. So that's basically what you've got. Those are your options here. And so make sure you are following this basically the way I have it laid out right here. Okay, so bring words down to the right, convert up. Words down to the right, convert up. Words down to the right. Okay? When you're doing stoichiometry, you always, 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 always have to have a mole ratio, no matter what. If you notice, in all of my 3 options, this one is always included. Okay? So you have to have a mole ratio. This is where you use your coefficients. When you have a mole with a gram like this, it's always a 1 mole. And this is always a molar mass. Okay? So hopefully that kind of helps. This is usually given to you. All right, next, CHO problem. All right, so I will probably post another one tonight that'll go a little more in depth. I'll go over the AP question with you, to be honest. But what you're looking for usually in these kinds of problems is you have a combustion. They tell you how much carbon dioxide or water you're making, and you go from there. So you would always want to set up a mystery thing, put it in excess oxygen, you're making carbon dioxide and water, okay, unless they give you another thing that you're making, okay? They will usually give you this value, they'll usually give you the sample size, and they want you to figure things out. So the oxygen doesn't really matter to us too much right here. We are assuming all carbon becomes carbon dioxide. Okay, and so usually when they give you the carbon dioxide, you start with grams of carbon dioxide. You're going to do the molar mass of carbon dioxide, which, by the way, hopefully you've memorized is now 44, to 1 mole of carbon dioxide. 1 mole of CO2 has 1 mole of carbon in it. And then if you needed grams, you would continue 1 more. 1 mole of carbon is 12 grams, the molar mass. Okay, that's always your first step. Okay, and then if you need to do it for water, you would do the same thing for water. Okay, but just be careful with water because there's 2 hydrogens in this. Okay, so this would look like grams of H2O. We would go 18 grams of H2O for 1 mole. 1 mole has 2 moles of hydrogen. And then we would say 1 mole of hydrogen is 1 gram, okay? And that'll get you those. Your oxygen always comes from subtracting. So now you're going to take your sample and you're going to subtract your carbon, you're going to subtract your hydrogen to get your oxygen in grams, okay? And that's the basics. Once you have everything in grams, we are typically saying find us the empirical formula. So now you want to follow your empirical formula steps. So you can go back in this video and look at those one more time. Okay? All right, classification of matter. You do need to know this just to make sure you haven't forgotten it. And tomorrow in class I will go over the separation of matter techniques, but honestly it was part of your summer assignment, so I hope you already have looked it over. I'll try and post a Bozeman video that'll help you with that too. So matter is split into mixture or a pure substance. Okay, pure substance is either elemental or it is a compound, such as water. An elemental could be something like this, or carbon, anything like that. Okay, mixture is either homogeneous or homogeneous, and heterogeneous. Okay, hetero, you can actually see parts. Homogeneous is also known as a solution. Okay, heterogeneous tends to be our suspensions. Okay, drawing a particulate diagram. So you need to know how to show a solid, liquid, or a gas. Remember, solid, you kind of want structure and things close together. Liquid, you can kind of loosen them up a little bit, but don't spread them out too much. They should still kind of be touching, just not as organized. And gas, you want to spread them out as much as possible. Okay, next you want pure substance versus a mixture. Pure substance, I should see the same thing throughout. Elemental will be one kind of circle. Compound is going to be more like you're going to have something mixed together, and I expect them to all look the same. Okay. Mixture, you want to show a distinction here. So if I have a mixture of a pure or an element and a compound, I would want to see it. And if it's homogeneous, make sure they are evenly spread. And if it's heterogeneous, make sure there's big differences here. Okay. Look over your periodic table. Please remember your charges, just like the +1, +2, +3, and so on and so forth, okay? Make sure you know how to use those charges in order to name things, so look over your nomenclature. Transition metals, you always want to use that stock system, so that means I do want you to look over your multivalent ions. I gave you a list in your notes, and like I'm going to post the key to the notes later anyway, so you'll see my list if you don't have it written. And then make sure you know who are your metals, who are your non-metals, because that is half the battle when you are naming. Finally, nomenclature. There is a video already on this. I'm not going to record that again. So I will repost it in this post so that you guys have it on Google Classroom right there. But remember, there's binary, there's ternary, we have acids. So there's a bunch of different rules. Just make sure you're keeping track of them. Molecular, use prefix. Ionic, you always end in "ide" or use stock system. Ternary, make sure you know those polyatomics. And that is it for the review. So I will get this posted for you, and the key should be coming up shortly.